Okay, say hi to Brandon, everybody. Hi, Brandon. Wow, we're sorry to hear you're sick. Wow, you're going to be so stoked about this lesson today. Oh, is that bad? Oh, man. All right, Stoke's theorem. Wow, Stoke's theorem is Green's theorem on steroids. Wow. You might remember Green's theorem before. Green's theorem said, hey, if you had a line integral and it was an enclosed region, we were able to find an alternate way to represent that line integral as a double integral. And we're going to talk more about that in due time. It's even on part of a review today on a worksheet. But let's go ahead and see what's going on here. Let's just say that we've got this higher dimensional version of Green's theorem. Green's theorem related, like I said, double integral to a line integral around its boundary curve. I think that's the big focus today, by the way. Boundary curves, you want to be thinking about it that way. Stoke's theorem relates a surface integral, a flux, if you would, over a surface to a line integral around, here we go again, a boundary curve. And you know what? Our author doesn't do a tremendous job on this. I wish he would have clarified things just a tad bit more. If we define boundary curves very well, I think it can really help you. And first of all, his explanation here is quite good. Let's just say that we've got this kind of hollowed out jelly bean, and this guy's walking around on the bottom, and you're walking around this figure, and you can see that we're oriented up. A positive orientation around a curve generally means you're going to be moving counterclockwise. You'd be moving so that the surface would always be on your left. Your head would be pointing in the same direction as the positive normal vector. But where our author really didn't spell this out, and other books have, and I think this is helpful, is that imagine that we were integrating down below to a curve C1, and maybe I should have made this a tad bit bigger. Imagine that C1 is the curve on the xy plane, so that we could generate that surface integral if we made a double integral integrating directly above it. What are we really getting at? When we're talking about a boundary curve, we want that boundary curve to be such that it would correspond to another boundary curve down below that would be like a shadow, if you would. That would have the entire figure almost like a little collapse kind of a cross section, if you would, down below. And that curve is so special. Let's take a look at the box here and see where we're going with it. We're saying that S is this positive oriented curve. We're saying, hey, if you wanted to find that line integral going around that boundary, well, it would be the flux of the curl of F. The flux, the surface integral over a vector field, but not over F itself, but the curl of F. Wow, we don't have time to prove it. Frankly, the proof is very, very difficult. And the author even glosses over it, saying we'll deal with the very generalized sense of it and leave the full proof of it to higher courses. But this is kind of neat. Let's do two examples today. Let's just take a look at a figure. Say that we want to find this line integral F, where you've got your force, F is given as written up here. C is this curve of intersection of the plane, y plus z equals 2, and the cylinder, x squared plus y squared equals 1. So what we're seeing is you could have done a line integral of f dot dr weeks and weeks ago, back in December. We even dealt with some of that on that quiz right before we got out for winter break. But an alternate way to do that is, of course, to work on the right side. We're going to say sometimes you might say, hey, you know what, it would be rather difficult to find a parametric equation for that curve. Maybe instead it would be easier to find the flux of the curl of f on a certain surface. The surface that's enclosed by that boundary curve. So we could say, hey, let's look at this surface perhaps right here. This might be the easiest surface that we could envision, thinking that's enclosed by that boundary curve. And my goodness, as we do that, let's quickly remember how to find the curl of f. Wow, the curl of f, guys, you're going to have to know how to do that. No doubt about it, part of your final will have finding the curl on it. We said right out I, j, k. What would be next? Yeah, partial derivative. This is your del operator, if you would. Yeah, absolutely. Partial derivative with respect to x, with respect to y, with respect to z. And then underneath, we have our p, q, r, if you would. We could say, oh, here's our negative y squared, our x, and our z squared. And once again, we could hopefully quickly come up with a curl here. And we could very much see that we could say, look at this right here. We could, and I'm going to write it out in bracket notation. Tell you what, cross out the first row, first column, and you're going to be left with this 2 by 2 determinant. Now, it only will take a moment for you to say, hey, what's the partial derivative of z squared with respect to y? 0. Hey, what's the partial derivative of x with respect to z? 0. So we'd have that first diagonal minus the second. You'd say, wait a minute, that's just 0. You bet. Okay, well, let's move on to our j component. Well, our j component, cross out that middle row. Remember, we'd actually have a minus in here. And then we'd say, well, what's the partial derivative of z squared with respect to x? 0. And now we'd say minus the partial derivative of negative y squared with respect to z. That would also be 0. So you'd have 0 minus 0. You even have a negative out in front of it. You'd say, wait a minute. My j component is 0. Yep. Wow, get a load of that. Sometimes kids are like, wow, will the last thing be 0? Will the last component of the curl vector also be? Well, we don't know. Well, let's see. Oh, this is going to be different, isn't it? Thank goodness. Didn't want this to be too boring here. Look at that. We've got the partial derivative of x with respect to x. That's 1. And then we'd say minus the partial derivative of negative y squared with respect to y. What's that? Yeah, negative 2y. So it's 1 minus negative 2y. All of a sudden, kids will say, hey, that becomes, very simply, 1 plus 2y. Okay, look at that. That's your curl. And at this point, we could very quickly say, well, hey, I'm well on my way to working this out. I could very quickly say, like we just did going over the homework, that I'm going to find this flux. I've got the curl of f, and we're going to write that in here, dot ds. I hope you remember how the curl of f is going to work out. We're going to get to that in just a second. First, we've got to have a surface, though, that we're talking about. We have to say, hey, there should be a surface that boundary is enclosing. Any ideas what might be a very nice and simple surface? How about the plane? How about z equals 2 minus y? And at this point, we could say, well, wow, if we had that, remember yesterday as we were talking about surface integrals over vector fields, that is with flux, we had 2 different forms. We had surfaces that were parametrically defined. We did a homework problem with a sphere just a minute ago like that. And then we also had problems where our surface had a function defining it. And that's what we have here. So I hope you remember this function form. It was negative p times partial derivative of g with respect to x minus q partial derivative of g with respect to y. You guys remember how we ended it? Plus r. And sometimes kids are like, well, yeah, that's fine. I guess I know what the partial derivative of g, call this right here. What's your partial derivative of g with respect to x? That would be 0. Hey, what's your partial derivative of g with respect to y? You might say, where are you taking your partial derivatives from? Oh, right here. Z equals 2 minus y. You know, what's the partial derivative of z or g with respect to y? That would be negative 1. And sometimes kids are like, that's not my question. I think I know how to deal with that surface and its partial derivatives. That's all well and good. Sometimes kids are like, what about the p and the q? Should it be the p and the q up here that we had for the force vector? Actually, no. Because we're not putting f inside of that integral right now. Technically, this is the flux of the curl of f. So if I may, I'm going to say, redefine this as p, q, and r for the curl. Why did I write p, q, and r in the beginning? Well, just to say sometimes that is in general how we think of vector fields. Don't get me wrong. But what's going inside here? Well, let's see. We've got 0, negative 0 times 0. And then we could say this is minus, well, what's our q? Our q is 0 times negative 1. Oh, would you look at that? And how about our r? You could say, well, my r is 1 plus 2y. Wow. All of a sudden, all of that just wipes out. I'm almost done. I've just got to deal with these parameters right now. And, of course, that's with x and y. And like I said earlier in the lesson, you want to envision this boundary curve to correspond to a curve down below also. It's as if we could shine a light and get a shadow and say, that boundary curve has to correspond to the region that we would be integrating over. And I hope you can see very quickly and say, wait just a minute, that's the circle x squared plus y squared equals 1. Well, why is that so important? Well, I could integrate with a dy and a dx, and that's all well and good. What's an alternate way to approach this? What, polar? Yeah, you know it. So tell you what, going to polar, we're going to say, you know what, I'm going to integrate. This becomes 1 plus, well, my y here is going to be 2r sine of theta. But then I'm going to say r dr d theta. And what do you think my r is going to span from down here on that xy plane? I'm going to go from what to what? 0 to 1. And how about theta? We're going to go from 0 to 2 pi. Look at that. So at this point, I'm going to quickly make a statement that the calculator would probably be the easiest way to arrive at this answer. Of course, we could work it out by hand just as well. Guys, that's going to be an answer of pi. I'm going to say by a calculator. But wow, do you understand what you just found? You're saying that not only is that double integral the answer, you're saying that that line integral up above would get you the same answer. The line integral would get you the exact same answer. So that, guys, is very, very powerful. Let me tell you the truth. Sometimes, rather than work out a flux integral over the curl vector field, sometimes you'll want to do a line integral instead. Both ways are correct. Both ways will get you the same answer. But it's which one is easier? So let's take a look at the next